So I think recording is started now. Most likely, yes. So to summarize, to recap very quickly, I think what I have discussed were the two transport phenomena that exist within the semiconductor. So basically, one is, as mentioned to you, one is your drift. The component of the current that may constitute is a drift current. So this is basically because your thermally generated carriers. So carriers, I mean to say both together, right? So whenever there is a covalent bond, whenever there is a break of covalent bond, so it releases the electron hole pair together, and then because of thermal energy which is supplied to the system, it's the electrons or the holes move randomly, and when you apply an external electric field or presence of, let's say, presence of electric field, give certain drift, so make them for possible drift certain definite directions, right? The another one component is your diffusion current. So basically it has been so if there is an asymmetricity into the concentration gradient, so the flow of charge carriers from high concentration to the low concentration, so it's basically flow of charge carriers from high concentration to the low concentration, right? So if we take a, let's say, p type block, let's say if this is a p type block, so with the basically you have the holes. I'm just drawing the charge carriers, majority charge carrier, let's say holes which are, so let's say this is low concentration area and this is high concentration area. So the holes are represented with the open circles here, right? So what's going to happen? So there's a concentration gradient something like this, let's say. So the holes as it started migrating, it start moving from the high concentration to the low concentration, right? And if you have, let's say, n type block, this is an n type block, this is a filled circles, and let's say and might be some minority charge carriers might be present here, some minority charge carriers, let's say electrons in this case, in the p type block. So this is the n type block. If its concentration gradient is like this, right? So the electrons from high concentration to the low concentration, so that's a diffusion, right? So this is a diffusion. And also now what other than this concentration gradient, since you are supplying, yes, so some noise is there, so this will be also recorded. If you unmute yourself unless there is a question, it will be recorded. So if you have a question, you can unmute yourself anytime and you can ask me anytime. But if you, that will be also kind of like any noise, it will be part of this. Yes. Okay. So this is a, let's say, p type, n type. So there's a diffusion that takes place. So other than this, because since you are let's say working at a room temperature, so there may be a kind of like because of thermal energy which is supplied to the system, the electron hole pairs might be generated because of this. So those are kind of random in motion. So I think that's I'm going to explain a little bit further clear. So this component, so if you look into, if this is a if this is a concentration gradient, if the holes are moving into this direction, electrons is, let's say, moving from here to here, so it's constitute a current, let's say IH, due to holes, and since electron is coming from this direction, from high to low, right? And so the electron comes constitute the current like this. So the current component, because of the diffusion, it would be simply a sum of both IH plus IE, right? It is a because of the whole movement, and this is because of the concentration gradient of like this system. So now when I combine, let's say, when we grow this PN junction, combine, I mean to say pictorial here, but when we, let's say, deposit, when we fabricate this device, basically you have the a type of substrate, a p type substrate, in the sense, let's say, where doping has been done, and then you grow the n type on this top of this. So you bringing simply pictorial way. What I mean to say here, that you are having a So here is the, let's say, the holes. So the background, because of the p-type region, so basically it is a, so this is more, and my is a high concentration, low concentration, and then you have some minority charge carriers, let's say the electrons. This is to represent only, right? So this is a p-type and this is an n-type. So we have the, just hold on, something is wrong with this touch screen now. Just hold on for a second. I think there's some issue with this touch screen. Right, on the this side we have the electrons. Let's say there's a highly dense on this side.
Hi.
Hello, please don't unmute yourself. And some minority charge carriers. Right, so what's happening at, let's say, is at t equals to 0, since because of concentration gradient, the holes started migrating from the, this is the p side, this is the n side. Holes started migrating from p to n side region, where the electrons, because it is a concentration gradient is high on this side, so started moving on this side. So let's say it's happened at t equals to 0, t equals to 0. And as the next, so what's going to happen because of this process? Because of the diffusion, so what's going to happen, it reaches to the, as it's they crosses, right? The started diffusion takes place unless certain point. So at, let's say, t equals to t1, in this process what's going to happen, because these are the positive charge, and since it's balancing the charge by the acceptor atoms, so basically they are on this process, they are uncovering the bound charges, which are nothing, these are the acceptor atoms. And same thing happens for the n side. The n side is a basically donor atom, so we have the major charge carrier, let's say the electrons on this side, and here the holes, which are the major charge carriers on this. And then you have some minority charge carriers, right? And this are the holes on this side, so with minority charge carriers. So after some time, let's say after some time, hello, yes, speaking. Who is speaking? Right, it's because t equals t1. So what's happened? So we'll see that this region specifically, this region where you get the bound charges, which are the acceptor atoms on the p side, whereas donor atoms onto the n side. So the region actually surrounding this region is basically, it's depleted. So is become depleted for the free charge carriers. So free charge carriers on this holes. So this region is basically depleted region, and the same for here. So this region from here to here, this region where there's the absence of let's say the free charge carriers. So this region we call it depleted charge region or space charge region. And this gives rise to, now what's going to happen? So diffusion going to stop because of the presence of the electric field, inbuilt electric field, or the, let's say, the internal electric field, which is being generated because of the this bound charges, right? These are the, because of this bound charges, so the internal electric field is being generated, and thus this opposes the flow of further, or let's say the further diffusion. So it means from the p side, the holes cannot now cross this junction, and from the electron from the n side, now it cannot cross this junction. So this opposition, right? So at this if we look into this position at this moment, since you are not giving any external external biasing here. There is not applying any external voltage here. So it means the current which comes from the, let's say, diffusion, and should be equals to the current due to the magnetic charge carrier. So I'm going to talk on to the, let's say, what's mean by so this is the component due to the diffusion, and this is current due to the magnetic charge carriers. Magnetic charge carriers, again, these are whole. So because of the as I mentioned, because thermal energy, because of thermal energy, the what's going to the electron hole pairs, let's say there is a covalent bond breaks, let's say in n type, so you generate a one electron, one holes, let's say, being generated, and this because of thermal energy, let's say, what's going to happen, this may cross, let's say this will be holes which might be onto this side, may diffuse, they start may diffuse towards edge of this space charge region or depletion region, and because of the presence of the electric field, because of the presence of this internal electric field, these holes may be swept away. The holes may be swept away to the p side region. That constitutes your minority, the current that's due to the minority charge case, because these holes are minority in the n side region. Same way, if we look into the p side region, or say p type material, where the, let's say, if there is a break into the electron hole pair, let's say somewhere here, so the electrons which are minority charge carriers onto the p side region, they diffuse towards the junction, and with presence of the electric field, they get swept away across the junction. So that, of course, is considered very low. Low means almost negligible. So the so but under, if there is no external biasing condition, so under thermal equilibrium condition, the component, or let's say current component, has to be equal. The component due to the diffusion has to be equal to the component due to the, let's say, minority charge carriers. This is component coming from the thermal generation of the charge carriers, and this component is coming from the, because of the concentration gradient. The ID here, this diffusion component is strongly depends on this potential barrier. Potential barrier voltage, whereas the IS is basically, is of course, because thermal energy, so is basically temperature dependent. So if I look into this potential barrier, so let me draw a very clean diagram once again. So you get the negative bound charges, right? These are holes on this side, electrons, and some minority charge carriers. So this is electric field here, E. So if I look, so this potential barrier V naught or VBI, so that's an potential on the U, and this X on this side, and this built-in potential, this we call as an the resultant electric field, or let's say the potential, we call as a built-in potential. So sometimes you see the VBI mentioned, and that depend on to, of course, the doping concentration of the both the region as well thermal. So we can write down this expression for built-in potential is your VT natural logarithmic ln n a n d, that's a, and then ni square, where na is your acceptor atoms concentration of acceptor atoms, or let's say concentration of the trivalent impurities, where nd is your concentration of donor atoms. Now what you see, and I is your intrinsic carrier concentration, and this Vt is your kBt divided by Q. So kB is the Boltzmann constant, T is the temperature measured in Kelvin, Q is the charge of the electron on hole, right? So this is a 1.6. So what you see here, this built-in potential, it depends onto the doping, onto the doping concentration. It depends onto the intrinsic carrier concentration, and this intrinsic carrier concentration here, Ni, it also depends onto is temperature dependent. Is a temperature dependent. If you recall it, Ni square is some BTQ exponential minus KB. KBT or what? Yeah, anyone remember it? Okay, I have unmute. You cannot unmute yourself right now. So that number comes to be minus EZ by KBT. Not this is EZ by KBT. Right. So Ni is a temperature dependent. So as you see that this built-in potential, this number for silicon. So for silicon, if the p-n junction, let's say p-n junction is made from the silicon, let's say if you're using silicon metal, since both are silicon, so p-type, n-type, both are in the silicon platform. For silicon, this built-in potential is approximate, goes from 0.5 to 0.8 depending on to the gain onto this numbers, right? So for standard doping that we use for the normal electronic diode, or let's say used for the rectification, not high power diode, let's say for the standard use for the electronic diode. So standard doping profiles, 10 power, let's say 10 power 17, and is 10 power 17 per centimeter cube. Same way, maybe 10 power 17 for ND. And if you just substitute Ni for 1.5 10 power 10 per centimeter cube, if you would like to, you can calculate also for room temperature. This number, let's say, if you substitute all these parameters, right, so you can approximate, it comes to be 26 millivolt at room temperature, let's say at 300 Kelvin. Exact number is 25 point something, but this is less approximate 26 millivolt at the room temperatures Vt. So if you are changing the temperature, so the built-in potential is going to, what's going to happen if we increase the temperature, built-in potential is going to slightly decrease. Same way on to the, if we increase the doping concentration, if we increase the doping concentration, this is also going to slightly decrease. So if you have highly doped, let's say p-n junctions, if you heavily doped, let's say if you heavily doped the p-type or n-type, that may be asymmetric also. So basically when we represent this heavily doped, we always put in a symbol of plus than this normal or n plus. So it means this concentration is higher than the standard doping concentration. If you do the p plus plus, or if you write n plus plus, so it means that these are the heavily doped, right? So this also going to decrease, so built-in potential going to decrease. So for case of the germanium, when we make these diodes from the material germanium, this built-in potential again is go from 0.2 to 0.4 volt, sorry, volt. All right, so any questions? Let me. Any questions? Do you have any questions? No?
What does V bulletin signifies?
What is built-in? So this built-in is a voltage drop across this region. So there is a certain, it means this is a let's say W depletion width W, since it's in a built-in is because of the presence of let's say presence of mirror, because of the uncovered bound charges, so it gives rise to internal electric field. So this is a certain width is there, so there's nothing is a voltage barrier, voltage drop across this region, across the depletion width. So this we call as a built-in potential.
Okay, sir.
This we call as a built-in potential. Yes.
Sir, what is the difference between thermal generation and drift current?
Okay, so the basic difference is because there is a you we make a profile concentration gradient profile in such a way that so there's a we make a doping profile in such a way that there exists in a concentration gradient, right? Whenever so it means whenever there is a movement because of concentration gradient exist here. So the holes, let's say, go from high concentration to low concentration, or electron can move from high concentration to the low concentration. So whenever there is a movement of, or let's say, movement of, or let's say, movement of these charge carriers, so it constitutes the current, right? So the current component, which is coming because of the concentration gradient, we call as a diffusion, because this process we call as a diffusion. So the component of the current is because of this is called as diffusion current. Now, because let's say you are working, if it is in a that's you increase the temperature, let's say if because of, let's say, even at the room temperature, so they're going to the covalent bond which may break within a, so let's say if I consider a block here, so let's say this silicon, so let's say this is antimony for example, and silicon antimony. So what's going to happen, let's say this covalent bond breaks down, cross means I mean representing the it breaks down. So what's going to happen is going to generate one electron and one hole pair is going to be generated, right? Because of thermal energy, because of the thermal energy. And so this is going to be scattered, is going to collide with this parent atoms. Maybe this is the donor atom because of the it donates electron. So these are the plus sign means nothing, this is a all these are the donor atoms, right? And so this is a give rise to the electron hole pair generation because of the thermal process. So and it's going to diffuse if the let's say it's going to diffuse, let's say it reaches to the junction, the whole has a tendency, so it reaches to the junction. So what's going to happen here, it reaches to the junction, it's maybe swept away, it will be swept away by the presence of electric field. It's not that all the holes which are crossing and the electrons are crossing, they all crosses the junction and reaches, let's say, before the built-in potential before this before the establishment of internal electric field. There might be some recombination may take place between electron holes, so that may again give rise to the some energy, heat energy to the system. So some recombination may also take place between holes and electrons, right? But majority of, let's say, majority of the holes which is from the p side crosses, it goes towards n side, and majority of the electrons that crosses it goes from n side to the p side. You get my point? So diffusion we actually we created, but the component thermal is your, let's say, intrinsic behavior, and diffusion is coming
Yes, sir.
because of the that we have created the system in such a way that.
Sir, actually, what I asked is that here, here you have written that thermal generated current, that
Yes.
is drift current. But previously in the slide, it was written that it is due to electric field like that. I mean, what is the connection between these two?
Yes, there was some intermittent internet. Can you once again? Can you say once again? Fraction of second there was
Sir,
a disconnection.
I said that
Yes.
I have not asked about the diffusion current, that I understood, but I am asking about the drift current. In the drift current,
Yes.
in this the previous page you written that it is thermally generated carriers, and previously in
Yes.
the slide it was written that it is due to electric field. So what is the
So
connection
I mean
between
like
these two?
so okay. So this is electric field means like if you see this whenever there is a if you are having a this is a all random, right? This is a all random. Average net flow is zero. Average net flow charge is zero. So if I apply in a field, if I apply in a field, electric field, external electric field here, right? So then it gives a certain its drift component is added onto these charge carriers. So it is coming because of thermally generation. I mean, like the carriers which are generated thermally, since it's a random motion. But now when you, let's say, apply an electric field externally, so it gives a certain definite direction, give rise to certain let's say some definite amount of current, which has not been the case if you do not apply any external electric field. So what I mean to say here, kind of like uh, the charge carriers which are being generated because of thermal energy, thermal agitation, that may constitute the drift current because you are applying certain electric field. But in case of the diffusion, it is not the case. It's simply charge flow of charge get from the high to low concentration.
Okay, sir.
Okay.
Yes, sir. Okay.
I mean, like there is won't be any average flow, let's say average net flow of the charge if there is no external electric field. There's simply zero because of random motion. So if you take an average that you put up any time, or let's say an a particular cross section area, so what you see actually average flow of charge is zero simply. So it's not useful. So if I apply an electric field, if you then in that case you're making some useful that give a certain definite direction and give rise to some finite amount of current, a flow of charge. So that constitute the drift current. Okay, so any other questions? And we can express this depletion width. Basically we can write down again is in terms of 1 over NA plus 1 over ND and built-in potential. So what you see here, the depletion width generally for this standard doping profile, this number is basically is go from 0.1 micrometer, it can go up to the 1 micrometer. You can substitute an epsilon s here. Epsilon s is simply the dielectric permittivity. Of silicon, because you are preparing from the silicon material, so it means epsilon s simply your 11 point something or 12 or around 12, but exact value is 11.7 epsilon 0. So if you substitute this number, let's say if you take Na is equals to 10 power 17 per centimeter cube, if you take Nd as an let's say 10 power 17 per centimeter cube, if you take this number equal, if you take Ni as an 1.5 into 10 power 10 per centimeter cube, and that's what you needed. Epsilon will you can find out VBI. So this you can also find out KVT ln Na Nd by Ni square. It will good practice if you can just calculate it. For following number you can obtain the VBI, this for the silicon, and then you can obtain the depletion width. So what you see, once since is a the another one characteristic, since the width is there, so charge there is an accumulation of charge and one side plus positive charge, another accumulation of charge is a negative on this side. So this region can act, so it means we can turn the PN junction to a capacitor as well. So that's, I think, when we go into discuss into reverse bias configuration, when we do the biasing, right now there is no kind of like a biasing, that we are not applying any external voltage, so it's just explaining the process. Right, now to make it useful, so to make it useful, now what we're going to do, we apply external voltage here. We apply external voltages. External voltage means simply which we call as an biasing. We apply an external voltage, so it means simply a biasing. So if we look into the, so the two situations, and let's say this other, there is some ohmic contacts, this metal contacts to make it the wire. So this is a P side, this is the N side. If P side is connected to positive and N side is connected to the negative, so this kind of like a biasing condition we call as an forward biasing, and another one is so another one is if we connect the This is a negative. Ohmic contacts on this side here, and P side is connected to the negative terminal, and plus terminal is connected to N side. So N side and P side. This situation we call it a reverse biasing. Right. So let's look into the. So when we and there is no if for open circuit condition. Open circuit means no biasing. Then in that case your ID is equals to IS, right? So because of the thermal equilibrium, and whenever you connect the external voltage, so what you have now, so what is going to happen, since it's in a inbuilt is, let's say film writing is in a internal, and let's say this is your E external, so which is on this direction plus 2 minus. So what's going to happen in this case? Now can you come up with your ideas what we have discussed based on this one? If I connect it externally, that's in this whole process. And you like to say anything? What's going to happen in this case?
At low voltage, the current will be 0.
Yes.
But at higher voltage, it will be.
Yes, as you so there is an built-in potential. Yes, true. So as the voltage, let's say the at here, as it reaches, let's say if you don't apply, if you apply say 0.1 volt, there is you don't see, because still the this potential barrier opposes the flow of or diffusion of the charge carriers across the junction. As it reaches to the, let's say the number as goes to the 0.7, right? You see some small, but as soon as I'm talking about for the silicon, as soon as the this V external, let's say, goes, it become greater than the built-in potential, let's say, which is a, let's say 0.7 volt. But you see that what's going to happen in that case? Yes. What's going to happen?
There will be drift current from P side to N side.
Okay. From drift current, and then the diffusion that couldn't be completed, right? Diffusion couldn't be completed. The diffusion will also take place. So that please, so we can understand that drift is coming because of your, let's say, thermally generated, those electrons which are being generated. So because of the, still, as I mentioned to you, this built-in potential, let's say potential barrier, is opposes the flow of charge, right? So what's going to happen? The depletion width shrinks, slight decreases as you increase the voltage. As you increase this voltage, external voltage, the depletion width slightly decreases. It decreases slightly, right? As you increase the, let's say, V external, the voltage which you applied, as you go up, right, depletion width decreases. So what's going to happen? There's going to be again the diffusion of charge carriers will take place across the junctions. Diffusion charge carriers will take place, and that would constitute the current. That would constitute the current, right? So I think as a numerical example, what you can do, you can try out, you can find out the component due to the, let's say, diffusion. I will give you the, let's say, one dn over dx, or let's say the concentration gradient. You can obtain the diffusion current for a given, let's say, doping profile, and you can also find out the current due to the drift component as well, given the, let's say, the value of the electric field, right? Is you can try out this in a part of, let's say, numerical exercise. We can do it into the tutorial as a part of tutorial as well. So what's going to this flow of the charge carrier across the junction that constitutes, so the holes from goes from here. So that means the IH move here, the electrons from here to here. So that constitute the current IE. So basically what you see here, your component, diffusion component, that's a dominant one. Actually, it's not that drift is not there, it's a dominant one. So diffusion current is, of course, is exceed, let's say, the IS current to the drift current. So it exceeds number, so it becomes, let's say, the current which flows into this into the circuit is because of the diffusion process that dominate, it exceeds. So this ID basically we write down as an function of, we can, of course, it is that we can obtain this ID is now as a function of IS exponential and VD over VT minus 1. So this is minus 1 here, and this is basically onto the profile. So basically for standard diode, electronic diode, for n is equals to 1, so is become simply VD over VT, and VD is the potential drop across this junction, so which is basically your built-in potential is around 0.6 to 0.7 volt for the standard values. So that constitutes. So how does the device looks like? So I think I can, so I don't have right now with me diode, but I definitely I would be happy to show you that. So it's if you want to find it out, so you'll see that's a black color. So two wires are coming out, and there's a kind of like a, if you have any charger, let's say mobile charger or laptop charger, right? If you open that box, let's say mobile charger, open the box, you can see the diodes. The 4 diodes might be there into that mobile charger, and you can, to identify it, you can see this is a one kind of like a stripe would be there, silver color. So that's we call as an N type. This means this faces to N type, and this is basically the rest is a P type. So N type is basically cathode, and this is P side, we call as called as an anode. And symbol for the device which makes out of, let's say, the PN junction is we call as a diode. So the straight line corresponds to the N side, the triangle line corresponds to the P side. So this is a plus and this is a minus. So we'll see that we learn it that we can replace this as simply as in a form of a battery. Of course, we can replace in form of a battery. Okay, so I think we'll discuss this on more detail.
Excuse me, sir.
Yes.
Sir, what is written inside of that EXP expression? EXP.
Okay, let me here NVD. I'm writing down. Let me write down on to the next slide. Just hold on. So this is basically the current ID is your IS exponential and VD over VT minus 1. So basically it's so N is a number, so this depend on to the doping. The basically for standard diodes, let's say we always use this N equals to 1. Is equals to 1. So ID we can write down simply equals to the IS exponential VD over VT minus 1, and this VD is nothing, is a voltage drop across the junction. So it's nothing, this is the value of built-in potential. Right, so what happens now, let's say when you look into the case of the reverse bias situation, when you go for the reverse bias. Yes.
So what is the n significance of n in this expression?
Actually, physically there is no significance. This only because of this measurement. This has been fitted number. That's all. There's no physical significance on this.
Okay.
Right. So, okay. And for the reverse bias, yes.
When there is bias, diffusion is still prominent. Is there any reason why?
Diffusion, because diffusion is still dominant because of the the concentration gradient is still, it is there, right? It is still there, and there's no, because of the, it started, diffusion started take place, and because of thermal equilibrium it stops because of the built-in potential, right? As soon as the depletion width is decreases, as we apply the external voltage, depletion width shrinks, so it's makes the charge carriers to flow again. They follow the diffusion process of those, the current, let's say, diffuse from high concentration to low concentration is that way. Whereas because the number of the because of the, let's say, I can say on other words, the number of, or let's say, the concentration carriers, because the concentration gradient is very high, right? Which is a less in comparison to the, let's say, thermally generated electron hole pairs, right?
So why the
Am I
width of
clear?
the depletion region decreases?
It's just because you're applying an external electric field, and this is an opposite direction, and if we look into the, so this is it shrinks. It's not that is completely elapsed, kind of like is no kind of like a is there will be still there, but it's not that it's become zero. But since you are the electric field here, the external electric field, if you see the direction, this is the inbuilt potential in this direction, where external field is in this direction. So this component is, of course, is higher, right? Is keep on increasing this component. So what's happening, the depletion width, because this flow of charge takes place initially, because of the built-in potential, it was stopping, it was opposing the flow of charge carriers, let's say, hold from the left to right, right? That's from p side to n side, whereas from n side to p side. So the holes which reaches to the n side become minority charge carriers, with the, and the electrons which goes from, let's say, n side to reaches to the p side become minority charge carriers. And other than this, there is a thermally generated. So what I'm saying, other than the diffusion, let's say there is thermally generated electron hole pairs will be generated from the both. It's not one side, it is in the both. So in, let's say, if there is a system here, so there is because of thermal generation, and that's getting drifted away because of the presence of the electric field. But it diffusion exceeds because of
Also,
the large concentration gradient. Yes.
sir,
Yes.
sir, you have
Yes.
shown in this diagram that holes are moving opposite to the direction of the applied external field, but holes are kind of positive, so it should move in the direction of external field. Why
So it is
it's
going to.
it's
So it
moving
is. I'm not saying.
opposite?
No, no. Where I mentioned this is going from p side to n side. I say
Sir,
p
but
side to.
the direction of applied external field should cause it to move in the opposite. I mean, in the direction of electric field.
Yeah. So it is going. So external electric field p. If we connect the p to the p side positive terminal, right? The holes cannot. If you look into the another way of understanding this, the holes cannot go to the, because there's a repulsion, right? So there has to be, they has to, let's say, they has to cross this barrier, because it's going to attract towards because the attractive forces to the negative terminal. If we go into the other way of understanding this system,
Oh, okay, okay.
right? So the holes are the concentration gradient profile exists, like say this, and concentration gradient profile of this, and onto the holes is like this. So there's a kind of like a, this is a concentration gradient. Let's say this is for the holes, and this is x. Let's say here it is x, and this is for the n p. Nice. So they exist. So doping profile has to be created. So what I am saying, like this is a man-made. What we are doing it, let's say, we need to create, because whenever there is a movement of charge, so we can move, or let's say transfer of the charge is also possible by the diffusion process. So diffusion is basically because you are creating a concentration gradient. So it is a kind of like a refabricating, like say it is an artificially done. But in case of kind of like a thermally generated process, which is intrinsic, because if you supply a system to the, if you supply a thermal energy, because of thermal agitation, covalent bonds break down, and that's goes random emotion. And if you apply a, because of if you apply certain electric field, right, so drift component is being added, because that goes into follow the field profile, field direction. So the force that is going to apply is simply QE, right? Simply it will go with that force. Am I clear?
Yes, sir.
Okay. Okay, so I think you can try out. Let me write down 2 or 3 problems. So I think then I can discuss the reverse bias, because this is very much important. Reverse bias is quite useful. So let me just give, I think, few kind of like let's say maybe you can fill up this table by your own. I would really kind of like, it will be good if you can try out what are the possible applications that you think forward biasing and reverse biasing. PN junction. It can be anything. So you can create a LEDs. You can create a laser diode by using a forward biasing sort of the system. Of course, you have the diode, normal diode, like for electronic diode for rectification. And in case of the reverse bias, and you can some more table you can.
Jenner diode.
Yes.
Jenner diode.
Yes, that's a reverse bias characteristic. So basically, yes, so you can have a Zener. Basically, do it reverse bias. Anything else? Solar cell. Anything else? Any other applications? Is basically is also you create a photo detectors. Well, this is for the energy for energy, and this is again for detector simply processing the information. And what else? So Jenner mean
So
like
thermocouple, PN thermocouple.
Yes, you can create it. Thermometer, diode as a thermometer also people uses, voltage regulator. Of course, thermocouple because the temperature dependent, very sensitive, especially into the reverse biasing. That's why right now probably I've discussed this on the, let's say, Wednesday on the reverse biasing. So and then we understand the some breakdown. So thermal couple, you can use the diode as a thermometer. You can create it for thermal. What else? Photo detector. This. What else? You can think of some more applications onto reverse biasing. Voltage regulation because of some fluctuations. So we'll see probably that characteristics, or let's say on Wednesday we'll discuss on those. You can create a source. So right now, that's I think as mentioned to you that you have the right now we are giving this kind of lectures, right? It is going from my computer to your different terminals. It is going, you are in different places across country, right? You are having a certain, somebody is using a mobile tower, some mobile connection, not tower, I mean there's some mobile connections, internet connectivity. Someone might be using through the other way of connectivity, maybe some at your place at home. So basically at background what is happening, it is your this device and this device. So you're creating a source. We create a source because of the forward biasing of PN junction. Of course, we don't use silicon. We use a gallium arsenide or some other material system. And for photo detector, we do have the onto the different material system. So this is one kind of like a live examples of, let's say, application of this PN junction that you can think of. So other questions we have, and I think then on Wednesday we'll start on to reverse biasing. Anyone do any other questions? Had to discuss anything? Yes. I stop recording.